What I'd like to do is to very briefly review some of the observations of auroral arcs, which is certainly one of the most dramatic manifestations of the coupling between the ionosphere and the magnetosphere, and then go through a very brief discussion of some of the theoretical ideas that have been proposed, but by no means all. I'd now like to turn to the plasma turbulence, which is associated with arcs, and I'm particularly going to just focus on those branches of plasma turbulence that we think, for theoretical reasons, have to do with the flow of field-aligned currents. On the same rocket shot from Baring and Moser and Kelly, they also had an AC electric field sensitivity. And this is a spectrum which was taken just as they entered the arc for the first time. You can see there's a sharp peak in the electric field spectrum, somewhere between 30 and 50 hertz, which corresponds roughly to the local oxygen cyclotron frequency. And the authors speculated that this is evidence for the excitation of the electrostatic ion cyclotron instability, which had been predicted theoretically by Kindell and Kennel some years ago. And at the same time, or very closely near to this, they measured a strong field-aligned flow of heated ionospheric ions. And they argued that this was essentially confirmed the theory, nonlinear theory of the electrostatic ion cyclotron instability proposed by Palmadesso and his colleagues at NRL, that instability ought to heat low-energy ions, and they ought to essentially expand thermally along the magnetic field and saturate out the instability by essentially heating the process. Another type of emission that's seen in aurora, and also seen essentially all around the polar cap, is VLF auroral hiss. This is a slide taken from Gurnett and Frank again, engine 5 measurements. These are the electron measurements on the night side, inverted V regions, day side, sort of just ordinary polar cusp-type precipitation. On the top, you see the 7 kilohertz channel out and all the way up to 70 kilohertz. Strong excitation of low frequency, or reasonably low frequency waves. Waves are primarily electrostatic. The spectrum generally peaks at the lower hybrid frequency, corresponding to the altitude of the satellite, but extends all the way up to 100 kilohertz and perhaps even merging beyond with higher frequency noise spectra. If you go a little bit farther out in the magnetosphere, we come to a region which has been very ill explored and will probably remain so until when the electrodynamic explorer mission gets off the ground. That is following the flow of field-aligned currents further out into the magnetosphere. Finally, there, of course, is the dramatic rediscovery by Don Gurnett of kilometric radiation, which was alluded to this morning. Here's a spectrum taken from one of Gurnett's papers. World kilometric radiation peaks somewhere between 100 and a megahertz in frequency, various other types of radiation that you detect. Has peak powers the order of 10 to the minus 15 to 10 to the minus 14 watts per meter squared per hertz. At those types of power levels, the total amount of radiation emitted by half a hemisphere would correspond to something like 10 to the 9th watts. And 10 to the 9th watts is just about what the average decametric radiation is from Jupiter, which is, of course, the EO-modulated radiation, and it puts the Earth in roughly the same power class as Jupiter, as a radio emitter. Now, this whole problem of field-aligned beams and their radiation is, of course, not just limited to the Earth. There are now 4 well-known and 1 less well-known object in the solar system which emits electromagnetic radiation by probably essentially the same process. There are, of course, the type 3 radio bursts from the Sun, decametric radiation from Jupiter, hectometric radiation from Saturn, and Brown has now recently, rumors have it, has seen 500 kilohertz radiation from Uranus. All of these spectra have a fairly broad range in frequencies, which indicate that the beams of particles that are making the radiation must have traversed a fairly large distance to have passed through a sufficient range of plasma parameters to account for the excitation of all the frequencies. So these beams must persist for a long time. And in particular, the case of the type 3 radio bursts, they've been seen all the way from the solar corona out to, in past, 1 AU. So solving the kilometric problem is, I think, one of very general significance for plasma physics in the solar system. And of course, one needn't stop there. Electromagnetic radiation processes exist throughout all of astrophysics, and we certainly expect from our experience with the Earth that field-aligned currents should also exist in many astrophysical objects. Those field-aligned currents may well take part in much of the radiation that we see from astrophysical objects. I think, however, that theory alone will not provide the complete answer to the kilometric problem. It's going to be necessary to go out, make observations in the generation region with an in-situ spacecraft. And I think, therefore, most theorists are looking rather forward to the Electrodynamics Explorer mission, which hopefully will fly right through that region with sufficient plasma detectors and wave detectors to tell us really what's going on. Well, with that, I'll stop.